Okay, so I'm going to start now. Last time I stated the Boreal localization theorem and I proved it. Okay. But then one student talked to me afterwards and I realized that, well, the proof wasn't quite right. You know, there's actually a mistake in it. So I'm going to fix the proof now. Okay. So the Burrell localization theorem says that if S1 acts on a manifold, M with a compact fixed point set, F, then the restriction homomorphism from the localized equivariant cohomology of M to the localized equivariant cohomology of the fixed point set is an isomorphism. And because the restriction is a ring homomorphism, so this is an isomorphism of R of U localized at U algebras. Okay, so that's the theorem. Okay, and the way we proved it is that because F is compact, it has a tubular neighborhood and F, and then it's an equivariant tubular neighborhood. So let NF be an equivariant tubular neighborhood of F. Okay. Then NF and M minus F is an open cover of M. And they are both G invariant. Okay. And so you have a equivariant Mayer-Vittora sequence. Okay, so the equivariant Mayer-Vittora sequence goes from HK minus 1 of the intersection to HK of M to HK of the two open sets to HK of the intersection and then to HK plus 1 of M. Okay. It keeps on going. Okay, so the equivariant Mayer-Vittora sequence is exact. And because localization preserves exactness, you know, I then localized with respect to U And then I said that because on M minus F, there are no fixed points, so the action is locally free, right? So this is 0. This is also 0. And this is 0. And so this is isomorphic to this. Okay, so that was the proof that I gave last time. All right, now what's wrong with that proof?
Well, each HK is not having price.
That's right, yeah. It's because, you see, each piece is an R module. It's a vector space. This is an exact sequence, of R modules, okay? But not of R of U modules. Because when you multiply by U, you increase the degree by 2. So it doesn't stay in this piece, you see. So each piece is an R module, but it's not an R of U module. You can't multiply by U. If it's not an R of U module, then you can't localize with respect to U. So yeah, so you can't do this, okay? You can't localize. We can't localize each term. With respect to U, because it's not an RU module, okay? So we have to fix this, but we can fix it this way. So the Meyer-Vittori sequence can be written in the form, you see, if you don't separate it into different degrees, then it's an R of U module. So you just collect all the terms together, you know. This is the direct sum of the equivariant cohomology over all degrees. Yeah. Then it's an RU module, and you can, this is a ring too, and you can restrict it to the equivariant cohomology of NF plus the equivariant cohomology of M minus F, okay? So you restrict the cohomology class to the two open sets, and then you can take the difference, that's the J star. So that goes to the equivariant cohomology of the intersection. And then there's a connecting homomorphism that goes from this to this, okay? And this delta increases the degree by 1. So you can write the Meyer-Vittori sequence like this, where all three terms are R of U modules, and the three maps are R of U homomorphisms. Yeah, this the restrictions, they obviously are U homomorphisms. But this delta, it's also an RU homomorphism. Okay? If you look at the definition of delta, you'll see that it is an RU homomorphism. Yes, so in general, if you have a short exact sequence of RU homomorphisms, then there's a long exact sequence in cohomology, okay, of RU homomorphisms like this. Okay? And I star and J star, they preserve the degree. So they are of degree 0, and delta is of degree 1. Okay? Delta increases the degree by 1. So all that it means is that if you write out each term as a direct sum, then see HK here will go to HK, and then this will go to HK here, but then this one will go to HK plus 1. Okay, and then this goes to HK plus 1, and then this goes to HK plus 1, and then this will go to HK plus 2. Yeah, so this triangle, it actually has many maps, right? This I star can be decomposed into a map in each degree. And similarly, J star and delta can be decomposed into a map in each degree. If you don't care about the R of U module structure, then this becomes a long exact sequence. Okay? But if you care about the R of U module structure, then you keep it like this, as a triangle. Okay? So this triangle is exact. In the sense that the kernel of any map is the image of the preceding map. Okay. But we keep it as a triangle, and we know that the action of S1 on M minus F has no fixed point, so it's locally free. So now, because these are all U modules, then we can localize with respect to U. Okay, so since each term is an R of U module, we can localize with respect to U. And localization preserves exactness. So, localization preserves exactness. So we still have an exact triangle, okay? And then because S1 acts on M minus F without fixed points, the action is locally free. So the localized equivariant cohomology is 0, and similarly, S1 acts on the intersection of M minus F with NF without fixed points, so it's locally free, so this is also 0, okay? So in this triangle, this is 0, and this is 0. And therefore, this is an isomorphism. Okay. So hence, I star from the localized equivariant cohomology of M to F is an isomorphism. Yeah. So it's really the same proof as before. It's just that this step about the Maya-Vittora sequence has to be written differently. Okay? Okay. Okay, so now let's apply this to figure out the ring structure of the equivariant cohomology of S1 acting on the sphere. Okay. Where? Where S1 acts on S2 by rotation about the z-axis. Okay. So we have this picture. There are two fixed points, P and Q, the North Pole and the South Pole, right? And we already know the module structure, so from the spectral sequence of the homotopy quotient over BS1 with fiber S2, and BS1 is CP infinity. Okay. We know that the spectral sequence degenerates, which degenerates at E2. So we know that E infinity is E2. And yeah, so I mean, we know that with real coefficients, this is just E2. with real coefficients, you don't have to worry about extensions because they're all vector spaces, so they're all free modules. So E infinity is E2, and E2 is isomorphic to the cohomology of the base tensor with the cohomology of the fiber. Okay. And the cohomology of the base is R of U. So this is R of U tensor with the cohomology of S2 is the exterior algebra. Let's see. I'm going to write it as, okay, it's the cohomology S2 is R, right, in degree 0, and then it's R times omega in degree 2, where omega is the volume form. On S2. And so this is R of U tensor with R. This is the tensor product is over R now. So R of U tensor R is R of U, and then R of U tensor with this is R of U omega. However, now this omega, it's a form on the sphere, right? So it's not an equivariantly closed form. See, and yeah, because d omega is 0, but dx omega by definition is d omega minus u ix omega. So, ix omega, yeah, I think we worked it out to be 2 pi, right? I mean, it depends on what you choose as your x. But in any case, this is minus u ix omega. It's not 0, okay? Yeah, so that's right. Okay, this is equal to that. It's isomorphic to this. Yeah, it's isomorphic to this, but this omega is not in equivariant cohomology because it's not an equivariant closed form. But we did find an equivariantly closed extension, right? I think we found that an equivariantly closed extension of omega is omega tilde, which is equal to omega plus 2 pi z u. Okay? Yeah, I think we worked out ix omega and we found that it was 2 pi z. So if you add 2 pi z u to omega, then it will become equivariantly closed. Okay, so if you want to have a generator of equivariant cohomology, here you should use omega tilde. Okay, I mean these are all isomorphic anyway, as R of U modules. Okay? But instead of using omega as a generator, you should use omega tilde, because omega tilde is actually in here. It's equivariantly closed. Okay? And so where omega tilde is omega plus 2 pi z times u. Okay? In the Cartan model, right? Yeah, these are all invariant under the z action. So an equivariant form, right, is a polynomial in U whose coefficients are invariant forms on the manifold. Okay, so this where omega is an equivariantly closed extension of omega. Okay? To say that it's an equivariantly closed extension means that it's an equivariantly closed form such that if you drop the u's, then you have omega. Okay? Okay. Now this is the module structure. Okay, so this equivariant cohomology is a free module over the polynomial ring with two generators, one and omega tilde. Okay? So in order to figure out the ring structure, we have to know what happens when you multiply omega tilde. You see, we have to know what's omega tilde square. And it has to be a linear combination it has to be a linear combination of omega tilde and u. Right? Okay. So now, instead of omega tilde, I'm going to divide by 2 pi. Okay, that's also a generator. We are working with R, so you can divide by any non-zero number. Let A be equal to omega tilde over 2 pi. Okay? Then A is omega over 2 pi plus ZU. Okay? Okay? And so So the equivariant cohomology of S2 is R of U plus R of U A.
Excuse me, I don't understand it's how you get the isomorphism from just omega to omega tilde.
From here to here?
Right, there will be Z, and it is not in the coefficients.
Okay. Now, I just multiply out the tensor product, right? So I get this. But now, I mean, this is, well, all that this says is you have two copies of RU, because we're looking, yeah, we're just looking at RU module structure here. Okay? So But the thing is that, so it's really just this. This just says this, okay? You have two copies. But what, you can write it like this, that's perfectly fine, but then this omega, it's not in here. Because this omega is the volume form on the two-sphere, and it's not equivariantly closed. To be in here, you know that you can represent this by the Cartan model. So if you want to represent elements of equivariant cohomology using the Cartan model, you have to use equivariantly closed form. And so this, I'm just saying that, okay, I have two copies of RU. I know that this is equivariantly closed. And right, yeah, yeah. And I actually should also show that it's not equivariantly exact. Okay? And the reason it's not equivariantly exact is that if you, well, okay, maybe I'll show that later, because if you integrate this over the two-sphere, then you integrate this, and you integrate this, but this is not a two-form, so its integral is 0. So the integral of this is the same as the integral omega, so it's going to be 4 pi, because this is the volume form on the sphere. So in other words, if you integrate it, you should get the area of the sphere. So it will get to 4 pi. So it's not 0. So you know that it is closed but not exact. Therefore, it is. It could be a generator. So, because you know, you know that you have a generator in degree 2 and a generator in degree 0, right? And so this is your generator. Okay. But you know, I decided to divide by 2 pi just so that I won't have a 2 pi there. It's just a z. Okay. Okay. So I'm not going to use A as the generator of degree 2. Okay. And now, so what this says is that as a ring over R, it's generated by U and A. Okay. However, you don't have A square. So A square, it should be a linear combination of U and A. So you should have a relation like this. Now, once you know what C1 and C2 are, no, just a minute. You should have a relation A square, no, just a minute. This is not right? Because A square has degree 4. So it should be a linear combination of U square and UA, right? Yeah. So once you figure out these two numbers, C1 and C2, then you have the ring structure. Because then you know how to multiply A square. Okay? So, the equivariant cohomology is generated as a ring over R by U and A. Okay. It's generated as a polynomial ring by U and A, and we need to determine A square, okay, which is a linear combination of U square and UA. Okay. Okay, so the way we're going to do it is to use the Boreal localization formula. Let me see. So so the fixed points, this fixed point set F is the set with 2 points P and Q. And then we have the restriction. Let's see. So the restriction. So we have an exact sequence. Okay. Kernel of I star here. Okay. Now, as someone pointed out, let's see, Boreal localization says that when you localize, these are isomorphism. So when you localize this, it becomes 0. Therefore, kernel of I star is torsion by Boreal localization. Kernel of I star, if you localize that, it's 0. So kernel of I star is torsion. Okay. On the other hand, we know that this is free, right? This is free. There's no torsion in here. It's torsion free. So since H1, since equivariant cohomology is torsion free, that means it has no torsion elements. So any submodule is torsion free. It's torsion free. That means it has no torsion elements. Okay? Well, how could it be torsion and torsion free? The only possibility is that it's 0. Okay. And so what that says is that, in fact, the equivariant cohomology of S2 injects into the equivariant cohomology of F. Okay? Now, the equivariant cohomology of F is just the equivariant cohomology of the 2 points. And so, so it's that's a disjoint union of 2 points. That's if you take the homotopy quotient, then it is the disjoint union of 2 copies of BS1, right? It's PS1, disjoint union PS2, PS1, QS1. Yeah. Take the homotopy quotient, and so this is the cohomology of PS1. That's cohomology of QS1. Okay? But the homotopy quotient of a point is the classifying space. So you basically get two copies. Okay, so it's R of U plus R of U. Okay, but to distinguish these two U's, because one is the U for the point P, the other is the U for the point Q. So I'm going to just put a subscript there, UP, UQ. Okay? And now let's look at the restriction of U. Now this U is the U for the two-sphere. Okay? So
The U for BS1.
This U, yeah, is the U for HS1, S2, okay? So, well, where does that U come from? I mean,
Does it come from the cohomology of C infinity?
right, yeah, so like if you have a manifold and then you map it to a point, then there is the induced map in equivariant cohomology. Okay. So this is R of U. And the U here, it comes from this U. Okay. Now, if you have a point P, that also maps to the point, and then this map also induces a map from R of U. So we usually call the U here by the same U, but in order to distinguish these different cohomology groups, so I call this PU, right? Yeah. Yeah, so here this U is in H2 of S1, S2, okay? And when I restrict it to F, I should get a multiple of this UP and a multiple of this UQ, right? And so can you tell me what this U goes to? So P is in S2, Q is in S2, and all these map to this point. Okay, so this is an inclusion. This is an inclusion. Okay, and yeah. So when you take equivariant cohomology, you see you have the equivariant cohomology of a point mapping to the equivariant cohomology of S2, and this inclusion becomes the restriction. Okay, you reverse all the arrows, right? Yeah, so when I restrict U, first I restrict it to P, then I restrict it to Q, right? I restrict it to the 2 points, okay? Now this is IP, this is IQ. Okay. And so this is IP star, this is IQ star, you see? And the generator here, it goes to UP here, it goes to U here, it goes to UQ here, you see? So what is IP star of U? It has to be UP, right? That by the commutativity of this diagram. Okay? U goes to UP. U goes to U, which goes to UP. Okay? So this is UP, UQ. That's the restriction of U. Okay? Okay, now. Oh, and then what is the restriction of A? So again, you restrict to P and you restrict to Q. Okay? And this is the formula for A. So what do you get when you restrict it to P? This should vanish because this is a two form. A two form restricted to a point is 0. So this should vanish and this should be? Yeah, Z is equal to 1 at P because P is the North Pole and U restricts to UP. So this goes to UP. Okay? And what about this one? IQ star of A. When you restrict this to Q, yeah, this is 0, and Z is minus 1, so you get minus UQ. Okay. Okay, so the way we are going to find the relation is that we restrict to F and find the relation in F. Okay, and because I star is an injection, then that relation will hold in here. Okay, and so what is the relation in F? in the equivariant cohomology of F. I mean, this is in the equivariant cohomology of F, and so is this, right? What is the relation between this element and this element?
The square of I star A is equal to the square of I star.
Yeah, so hence I star of A squared, because I star is a ring homomorphism, and then in the, this is also a ring, okay? And it's a direct sum, so the way you multiply is you just multiply the components. I star A squared is this, okay? And I star of U squared is also this. See, that sign disappears when you square. And so therefore, I star of A squared minus U squared is 0. Okay? And since I star is injective, so A squared minus U squared is 0 in the equivariant cohomology ring of S2. Okay? So you have a relation now. You have one relation, but this still doesn't tell you that that's all the relations. So we still don't have the ring structure yet, but I see that it is 4:20. So yeah, let's stop here and then take a 10-minute break, and then we can finish this problem. Okay, we still have to find out if that's all the relations that there is, so that we have the ring structure. Okay. Okay, so let's take a break for 10 minutes.